Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellyn, Illinois. And this video today is going to take a more in-depth look at the C++ Standard Template Library Binary Tree Class, otherwise known as STD::set templated type T. I'm going to be basically going out of the Jesutis C++ book. I'm going to be specifically looking at section 7.7, but there are plenty of other places you can go to see this information, and I have one of them open right now at cppreference.com, one of many places, and I have a Visual Studio project open so we can kind of tinker along. And so if you followed along with my previous videos, I've done vector, I've done linked list, I've done a lot of videos for a lot of different stuff, so I don't remember exactly what I've done, but since it's a standard and it's templated and it's a library, a lot of these functions I've already covered in different ways. So if I gloss over it, it's only because for my students and for me, we have already covered these topics 2, 3, or 4 times over. So what is a set? Excuse me. A set, according to Jesutis, which is very similar to what you see here, is a container that sorts the elements automatically according to a certain sorting criteria. And so we're just going to focus on set today, and the main focus between set and multi-set would be that, as we've discussed in my previous video, a set as a binary tree does not contain multiple entries or multiple elements of the same value, but in a multi-set you can have, like if I entered 3 and then 3 and then 3, there would be 3 versions of that inside of the set and the multi-set, but the set would not have the ability to duplicate those elements. So that's like the big one when it comes to that. Let's see. Uniqueness is determined by using the equivalence relation. Yeah, it gets under the hood, things get a little complicated because they're trying to make things simple for you or the end user, since it's a templated library and it's architected fairly, pretty well. When it comes to, you should not have to implement all 6 of the relational operators, less than or equal, greater than equal, not equal, and equal. You don't need to implement all 6 of them to get the value of all 6 of them, because I could do equals, equality, equal, and then from that I could just have not equal call that function and then just reverse the logic of it. So I don't need to supply, at least I only need to supply one of those 2. And I believe it's less than and greater than, it's like all the others can come from, I think, up to 3 different operators, which is pretty cool. So, trying to simplify matters for us on the back end of this thing. Okay, so creating sets, like everything else, there are the constructor, many different ways to go about it. That looks rather complicated. I like using the Jesutis book. I just love this Jesutis book when it comes to simplicity, and just different ways to go about it. I already included set up here, but to set up an empty set, I don't know, where the heck did the, okay, so a set of integers, I could say it's because I didn't put 2 colons there. Okay, so there we go. So then you could see if I run this, that gives me an empty set. And I mouse over things and I see size of 0, there's nothing in here. There's all this complicated stuff because this is much more complicated than a vector and all these other things. There's a lot more going on under the hood to make this thing work, as you saw from our high-level detail video, and you probably will see if you make it through the low-level detail video as well. So like, well, how I could also set up, here's the fun part here. Let me just put things in reverse order. 5, 4, 3, 2, 1. Am I allowed to do that? That's always the first question. Put a build and a rebuild in there, and yep, success. But what happens if I try to put this in, like, okay, there's my initializer list, 5, 4, 3, 2, 1, and I go B has 5 size, and oh my goodness, look at that, right? 1, 2, 3, 4, 5. Everything was reorganized. In a vector, everything would be placed 5, 4, 3, 2, 1. But what happens here is with this in this order, everything is put into the set, put into the binary tree, such that order is maintained every single time I add, remove, or change. So you can see here, so in this case, it's automatically, it's like, why would I use a vector when I use a set? Well, again, there's differences. But when it comes to sortedness, you get that ability. And so let me quickly just create a function here that prints out a set, and I pass in a set, const std set int reference, just call it A. And for every int I is part of A, I will cout I with a space. And then at the end here, I will print out the end line. I don't know. IntelliSense is a fun thing. Always lags behind. Okay, so I have myself a quick and dirty function that takes care of this, and I can print. Now I can print things out and see. I don't need a breakpoint anymore, so I can see this now. And oops, and there's my 1, 2, 3, 4, 5 as I'm showing, even though it comes in 5, 4, 3, 2, 1. And so just to kind of prove this, we're not going to discuss this just yet, but 7, I can do a b.insert, and I can say, okay, put in initialize. Oh my God, there's 8 different versions of this thing. How about I just can I put a 6 in here? And then do a print? Yes, I can put in the value. And again, notice now everything, that 6 has now been put in so that everything has continued to be sorted. Okay, so when it comes to this, there is my set. There is this copy constructor, of course. Remember, I'll do this every single time. There's a huge difference between something like this, which is setting up a set, and then saying something like this. There's, these 2 lines of code, as much as they look like they should be identical, are completely different in the eyes of the compiler. This uses the copy constructor, which means I'm constructing C on the spot right now in this moment in time, using B as the template in order to copy all the elements over. And this line, next line here, A and C are both initialized and constructed. So instead of using the copy constructor, it uses the copy assignment operator, otherwise known as single equals. And so it takes C and moves everything into A. It feels the same. It always feels the same to us on the back end of this. But if we're ever developing these things, we have to understand that it's 2 separate functions, and we can't really do much with anything else. So I can also go ahead here. Let me just set up. Let me include vector real fast. And I can set up a vector of ints, and I'll call it P, and then I will put in just random numbers. Oh yeah, let's put in the same number 3 times. Let's just put in some duplicate values and just get a hold of that. And so I can also set up a vector. Set up a set. And I can use, I'll call it D this time, and I can set it up using iterators. So we'll talk about iterators again. I've talked about it plenty of times before. But I can say, put in everything from t.begin to t.end, put it into my set, and let me get rid of this insert, don't care anymore. And how about I print D instead? And now you can see, again, everything is in sorted order. All the duplicates have been eliminated from the set. So all I'm left with is 2, 5, 8, and 9, and then the 10. Those are the only unique elements in there, and they are pre-sorted. So I can use iterators from pretty much any other collection, and they will, you'll go through, pull down the data, as long as the int type matches, right? As long as I have an int in both of the different sets, or different collections, set and vector, it'll pull the int out of the vector, push it into the set, and continue the ordering. Again, that's the whole point of this, is to maintain a sorted order inside of this data structure. It looks like pretty complicated, pretty weird data structure here. So initializer list handled. We're not going to worry about the move operators. We've got copy constructors. We've got just normal set and initializer list, and the templated methods with using the iterators. So constructors are pretty much covered here. So and we never have to worry about a destructor. Where's my phone? Sorry about that. I never have to worry about a destructor because, again, all of the newed up memory is destroyed automatically by its destructor. So we never have to explicitly worry about any of the data and any of the addressing, any of the memory stored under the hood, because everything that gets newed up inside of there will be deleted automatically for us. Okay, so capacity functions, empty and size. I mean, that makes total sense, right? If I wanted to, let's see, if a dot empty equals true, print out empty. And of course it should print out A being empty, and it does, because A at that moment in time has 0 elements. So if any time I put, oh, let's put 1 element in there, and it no longer prints empty, of course, right? So, and the same goes for size. And so empty, you know, same kind of deal. If size is equal to 0, then print empty. And size is exactly that, how many elements are in this thing, right? So, and I'm just going to have it print empty, even though, of course, it doesn't make much sense to print empty when it is 1. But you see that, because the size is just an integer quantity that maintains how many elements. We don't know, again, under the hood what's going on, but under the hood it does keep track of how many times we've inserted and deleted things, so it knows exactly how many of our elements are stored in its data structure. So that's pretty much, I mean, that one's simple, right? So then we can move up to the iterators. So the simplest way to kind of do this is to remove our range-based for loop and just use an iterator for this thing. So instead of printing out like this, we can just go ahead and say, I think it's complicated. I have a set of int, and I have a const iterator, and I'll call it iter, and I'll say it equals a.begin. So, and then, oops, and then I like to use while loops for this, since while a.end, or while iter does not equal a.end, and then print stuff out, I can do star iter here. So I have to take iter, which is an iterator, and I have to be able to dereference it to be able to get the information, the value that's actually stored under the hood. Because I'd be willing to bet for this set structure, this binary structure for inside of the standard library, it's using the same thing we've got, pointers for left and right nodes. Or maybe even more than whatever it is that we've got. So you need to be able to just get the information from that structure, and star will do that. And so I should be able to get back to exactly the same place, except, oopsie, this is the fun of using while loops. You occasionally forget to change your iterator here and to actually increase it, plus iter, so that my horrendously funny infinite loop now becomes right back where we expected it to, and it now prints out to 5, 8, 9, 10 because it's iterating through the structure. And so now, as a vector, it's going through one element for element. For a linked list, it's going through the linked list one element at a time all over memory. But with this binary tree, it's going down and down. You know, it's doing the in-order traversal from the previous video. So like that's exactly what it's doing. It's going as far left as it can, and then when it comes back up, it goes, okay, here I'm going to print myself out. And that's what's for every element in here, and it's printing out in order because of that algorithm that's being followed. So again, a lot of this is controlled for us. We get the in-order traversal for free, and it's not very easy to go ahead and do any of the other traversals because again, it's already controlled by the standard library. But I used const iter, and if I wanted to go backwards, I could do a reverse iterator, a.rbegin, and then I could say, well, iter does not equal a.reverseEnd, do something. And so now, like I say, this is a way to go reverse now. I can print in backwards, get everything from the back to the front. And I'm going to say, and if you want to, if I'm going to do that, I probably should use const reverse. Because there's 4 different types. Notice here, right? There's 4 different types of iterators. So const iterator, crbegin, and then as this does not equal crend, and you won't notice any difference. Constness is not something you actually notice on the back end. You only notice it as a developer with the code base. So I'm like, it's exactly the same, putting the const reverse in there. But just to show you then that there are 4 different iterator types. You should use the constant ones whenever you're doing something by read only, and that you hardly ever reverse anything. But if you're going to change stuff, then you should use the normal begin and end. Okay, so then, like everything else here, what else have we got? We've got clear. Okay, and so again, if I'm dealing with a set of pointers, I got to make sure, do I want to clear the pointers without deleting them? Yes or no? Because clear does not go ahead and delete any of and give back any of the memory stored under the hood. So in this case, if I have t and I do t.clear, yes, it'll clear all the ints out. But again, if it was pointers, it would not delete any of the memory that was newed up by those pointers. So I would have to do that myself. But otherwise, all the data gets cleaned up, and my t is now clear, so it should print nothing. A minute ago, it printed all sorts of stuff, but now it prints nothing because that 5-element set is now reduced down to 0 elements by clearing the thing out. Okay, so we've talked about insert. Insert is easy. You just put the t type in. What I just need to put an integer type in there, and it will figure out where to put it. So there's no push back or push front. It basically is a push insert, and it figures out where it needs to go, following the rules it needs to follow. So put it. Oops, I didn't mean to put a 49 in there. Put a 4 in there. Did I break something? Oh, t is a vector. No, that explains that. And so b down here, I'll just b dot insert. And I'm still printing out. I'm printing out D, so hold on. Now I can bring it back. Sorry about that. Let's print out something we actually see the difference here. There we go. There's my 19 and my 7 and my 4 and my 3 and my 2 and my 1. And again, by trying to insert 4 where 4 already exists, it does not duplicate that value, so it keeps the unique element stored inside of that set. So we're not going to do in place erase, exactly the same thing. Let's see, b dot erase. Let's see what we have access to. Now it requires a const int, so I can erase the 4 from it, a hard-coded number. And again, it doesn't remember that there's been 2 copies of it at this point. It just knows that there was 1 copy of it, and now it's erased altogether from the vector. So it's not like it maintains some kind of memory that goes, oh, you deleted it once? Oh, okay, we'll keep it for one more time. Nope. It's either in there or it's not, and then the erase operation goes from there. And so, like, if I could go ahead and say something like this. I want to delete all the elements. I can use iterators, and you have to be careful. Iterators of different types, because just to make sure, or iterators that are not the beginning and the end. You just got to make sure that they don't overlap, or they're not flip-flopped, or all sorts of things. But B is now clear again. It's just another way of clearing out, because it's saying start from my begin vector, go to my end vector, and delete everything in there, and it will just go ahead and find the values and erase themselves. So, okay, so that's pretty easy stuff, right? So let's talk about merge. So it looks like there's something very interesting here with the merge function. It is part of the C++ language as part of the 2017 edition to C++ 2017. However, I am not seeing this functionality, right? Like you can see that this, I mouse over this and it says that class set blah 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 has no member merge, even though it's screaming right at me. So you will see this, as long as you're living on the bleeding edge of things, you might see these kind of things where it looks like Visual Studio has not implemented merge for the set, for whatever that means, right? So we just kind of have to deal without it at the current time. And I had to deal with this out in the field too when I was working with the one video game company, because we were using a specific compiler because everything was so specific to the hardware, we were working on an old compiler. So when the 2011, the big 2011 edition came out to C++, all of that stuff, all those bells and whistles did not come with, at least for us. We couldn't use those things because we were still working with an older compiler. And the same goes right now. It's like, well, things are still catching up. I know it's 2020, moving on to the middle of 2020. Coronavirus is here and taking over a lot of stuff here. But it's still 3 years later. It appears that the merge function is not implemented, because it feels like I'm doing everything right, because it's a member function called merge, and I pass in a set, which I am. E is a set. And so it's taking that in as a standard reference, not const reference, but just a reference source, and nothing's happening. So at this point in time, I'd have to say, oops, we're gonna have to move on. If you know better than me, then put a comment in there down below. Send me an email. Let me know what I'm doing wrong, because at the moment it looks like everything is coming up normal. Should be in there, but it's not. So the last functions I wanted to cover are the modifiers, just some of them. We already looked at merge, which was the modifier that does not exist just yet. And we're not going to worry about extract or in place. So everything else has been there since at least the 2011 at this point. Oh, interesting here. You can even see here that the 2020 edition that isn't even out yet, as far as my understanding is, there's a function that's going to be called contains. That's going to be part of the new standard. So and again, just because people say this is part of the new standard does not mean that compilers have access to actually be able to do those things right off the bat. You know, it takes time and effort for someone to come up and to build these functions into any programming language, and so you can imagine merge just didn't make it just yet. Okay, so more modifiers here, or not modifiers, lookups. I want to talk about lookups. So yep, I want to do count, find, equal range, lower bound, upper bound, at least talk about them briefly. So count is exactly what you might think about this. If I say, you know, int whatever equals b dot count, how many times is there a 4? And let me just for the sake of this, let me put the 4 in here a few more times, right? Just to like, oh, in this case, you think, oh, there's 3 of them in there, right? However, we'd already discussed this, that I'm going to do a count on 4, and it's going to come back 1 because all those duplicate elements have been erased. So just for the sake of this, if I make this a multi-set, and again, I talked out just briefly, the difference between set and multi-set is essentially that a multi-set allows me duplicate values. So if I rerun this, those duplicate values now count. Oops. Let me just comment that out, since set, multi-set, nothing's agreement there. But you can see now this comes up as 3 because there's 3 elements in there of the value 4. So, you know, do you ever need that? I mean, basically, you could use a multi-set like a vector and be like, but then it sorts itself. There's a lot of different ways you could go about doing this. So for a set, though, just a normal plain old set, count is either a 0 or a 1, right? That just makes sense. So let's see, what does the find function do? b.find 4. Let's just see, what does find return? Come on, help me out. IntelliSense, help. Oh, maybe because I'm running. What does find do? It returns an iterator to a specific element. So what can happen? I can, oh boy, here, iterator time again, right? So I can say, okay, give me a set int iterator. I'll just call it I this time, is equal to b.find 4. And then what happens? Okay, so here's the fun of this here. Let's try to see out star I with an end line. And so it prints out, oh, that empty, stupid empty thing. Let me get rid of that. Let's start over one more time. So it prints the 4 like we're expecting because it finds the 4. But my question is, I'm setting all this up, what happens if I can't find the element in here? And then now we have, you can't see it on your end, but over here we have a debug assertion failed. We have an exception that got handled because that iterator is basically pointing to null. If you want to think about it, it's a null reference. So what does this thing return if it can't find anything? And it would return the end iterator. So even though I'm doing a search, I do have to do an if statement on the back end of this thing and say if I, or I guess if I does not equal b.end, then print out. So you have to do a little bit more work on the back end, and now it falls through. It does not crash on me. But let's go back and try this again. So just to make sure, put the 4 back in, and it should print the 4, and it does just in case. So this, you do have to do some extra work for this data structure when you're doing this kind of thing to make sure that when you're doing a find that you get back something that you can actually use. So yeah, what would vector do? Vector would return the same kind of thing. Vector would return an iterator at the end. Okay, so the last thing I want to do is talk about the ranges and the bounds, lower bound, upper bound, equal range. So you say for vectors and all sorts of things, like vector, I can get every specific element. I can directly go in and just get me the 5th element. I can't do that with a set. It's a little more challenging to be able to get in to find specific elements. So that's where the idea of the lower bound and the upper bound come from. And so lower bound is in essence, I can use probably either one of them when it comes to this because I'm using a set and not a multi-set. But the whole idea is I can get an iterator that will get me basically the closest value to whatever it is I'm looking for. Like, if it basically asks the question, if I were to insert whatever value into the into the set, where would it go? Where, like basically what where in the set, what iterator would it go so that it would add into, so everything is still balanced and equally fair. So just to show this, I can say, okay, let me just change this to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have a set of 10 elements, and it's completely ordered 1 through 10. And so I can get rid of this stuff now, and I can just say, okay, it's this lower bound function. And there is a difference between lower bound and upper bound, and it all just comes down to when you're talking about the idea of multi-set versus set. That's the reason why there's two different functions here. So the lower bound, get me the 2 for the I iterator, and then for the J iterator, get me the, I guess you could use lower bound for 8, and then just put a while loop here and just say while I does not equal J, print out everything star I, just like we did before with all this stuff, and what do I get? And then oops, while loop again. I infinite looped. It happens, right? I laugh. My stupid laugh, and I increment I, and now things are a little nicer because now, okay, see 2, 3, 4, 5, 6, and 7. Okay, so here is our rule. The lower bound did not give me 8, right? But if I believe, I don't do this very often, if I change this to upper bound, will it print the 8? And now it will. Because what? Because you got to look at the rules here. The lower bound returns an iterator, the first element not less than the given key, and then the other one returns an iterator to the first element greater than the given key. So yes, so completely different, right? The putting it before the 8 or after the 8 mean not printing the 8. And this is one of those off by 1 errors that we talk about often, especially with loop structures. And once you have the loop actually iterating correctly, and it's just to see that right on the edges, everything in between always works because it just we jump from one to the next to the next to the next. But it becomes a little different when we're talking about the beginning and the end and making sure we're hitting the correct beginning and the correct end, because this is how we have to do things if I wanted to get things in different values. So what if I go ahead real quick, just change a couple of these around and get rid of all that and try again. So now you can see, even though the set doesn't have a 2 anymore, it got me the place in the set it would insert into if I were going to try to put a 2 into there. And so it got me that iterator. So it's printing out the 3, the 5, and the 7, because those are the 3 values that are between the lower bound of 2 and the upper bound of 8. And so in this case, you could be lower or upper for either one of these, because, or maybe not for 2. Oh yeah, because again, just the before or the less than and the greater than can play a role, so you have to watch out for that. So if you're going to do a range, something like what I just did, I recommend then you do a set like that, or a lower bound for the low end and an upper bound for the high end, and then you're guaranteed something less than the value on the one end and then greater than the value on the other. But again, it all comes down to inclusive or exclusive on the edges, the fringe cases of the sets you're trying to maintain. And for real this time, this is the last thing I wanted to talk about. So I have a homework assignment that I give, the Yahtzee, like a Yahtzee problem. I give you 5 dice, and you have to tell me, using just sets and maps, just using the principles of sets and maps, tell me, and with maps is a future problem video we haven't covered just yet in this class, or in this, in my video series anyway. And so, so give me 5 dice, and I'll tell you what you've got. Do you have a Yahtzee? Do you have 4 of a kind, 3 of a kind, full house, large straight, small straight? What do you have? And so in this case, just real quick, I can say, okay, if it's a set, right? So we've discussed duplicates are eliminated from a set. So how would I ever know, as long as I'm putting in correct values of like 1 through 6, the values that a die, a specific die can have, if dice.size is equal to 1, I can print out Yahtzee. Because every single time, the first time the 1 got put into the set, and every time after it did not get duplicated in because it was already there. So in this case, 1, 1, 1, 1, 1 prints out Yahtzee because we have a Yahtzee. But if I make it anything else, that now the size will be 2 because now we have a 1. There's 2 elements in there, the 1 and the 2, so it doesn't print out Yahtzee anymore. So one little thing left then is to say, okay, else if, oh boy, here we go, dice.size is equal to 2. what to do, because like, what should I print? And this is where the fun of the homework assignment comes from, trying to figure out all these things and trying to figure out what's the differential. If the size is 2, I can't say it's a Yahtzee anymore, obviously, but there's only 2 cases this could be. And so I'm not going to go into all the details, but there's 2 cases, something like you see right here. It could be a 4 of a kind. That's this here. There's 4 of a kind and just a lone straggler that is not part of that. Or you can have this, where you have a full, what we call a full house, right? Because you have a 3 of a kind and a 2 of a kind inside of the same structure here. And so if I just continued on, this is full house, this is full house, this is 4 of a kind and 1 of a kind, and then this is back to the Yahtzee. So yes, there's one of 2 things can occur just off of this. And you go, okay, so if the size is 1, I have a Yahtzee no matter what. That's the only thing that it could be. But I have to differentiate between 4 of a kind and full house if the size of my set is 2 after I'm done with this. And so if you really wanted to, you could just continue on, like, if dice.size is equal to 3. Well, what does that mean for us, right? So that means there's 3 different things that could occur. So let's see, let's just 1, 2, 1, 1, 1, 2, 3, something like this, right? There's 3 different types of numbers in there. So it could be just a 3 of a kind. And so what else could it be? It could be 1, 1, 2, 2, 3. And so it could be 2 pair. And so, and forgive me, I don't, I'm just going through the motions here. Like, I would make sure, if I was doing this for real, that I would exhaust all of my possibilities. I would look up on the internet. I think there's, is it called probability genetics or something like Yahtzee? This is where I get my information from. When Yahtzee probability data genetics. So this is where I get my information from when it comes to this kind of thing with this kind of problem, is just to see, okay, for this, if the size of my set is 1, then it has to be a Yahtzee. If my set size is 2, it has to be 4 of a kind or a full house. If it's 3, then there's, okay, good, there's 2 pair or 3 of a kind, and I have to differentiate. And so now when I have a 4, say let's just finish this up now, just to say what have we got, since I'm already talking about it. The 2 things it could be is a pair, 1 pair, or it could be nothing. Because that's what this is. I'm sorry, no, size of 4 is, well, I guess it's just, no, it is 1 pair. Oh, okay, fair enough. It's 1 pair. Sorry, I got confused here. So 1 thing it could be, 2 things it could be, 2 things it could be. This can only be 1. This can only be 1 pair if there's 4 different values inside of here. And then otherwise you have, well, I guess, just to be safe here, just to make sure that the size is 5, you are guaranteed nothing. You're not, I'm not even talking about small straight or large straight. I'm just talking about the fact that with 5 different dice, there cannot be 2 matches because they're all different values. And this is all the probability, so Yahtzee is obviously very difficult to achieve, and the most probable one is the 1 pair. If you were to roll dice, about almost half the time, a little less than half the time, you would get 1 pair. Occasionally, if I played Yahtzee enough with my family enough, you can, it's 1 in 1,296 shot of getting a Yahtzee on your first roll, and I've done it. It's like, ooh, you do, right? But I've rolled the dice literally enough times that I've made that probability happen, and so is most of my family. So this is at least a good application, a starting application of a set to indicate, at least with these kind of dice, to get myself down. Again, not even to account for the large straight or the small straight, because you would have to do that in the 4 and 5 case. Because to have a small straight, you have to have at least 4 different values, and for a large straight, you have to have 5. So this could be 1 pair, or it could be a straight, or it could be both. Small straight, or both, question mark. And this could be nothing, or it could be a large straight. And so at least this broke things down for me, so that now now that I have a differential, and now I know it's one of these 2 cases, I can apply more questions to my data. I can do more analysis of my data to help me determine what is what here. And so And so maybe not a set, but if you had a multi-set or if you had a map, all these other data structures, like this helps get so far, but it doesn't help with the rest of the data. And I'm not saying this solution is the best solution, but I really like this problem that I give students because it just gets you thinking about how sets and maps work and how would I access the data to be able to get data that I could probably apply and get otherwise. How do I get this data and make it work? But anyway, I like this. I think it's pretty cool. And I appreciate you guys sticking it out with me again. This is pretty much everything I wanted to talk about for this video lecture. If there's any questions, did I do something right or do something wrong? Is there something you'd like to have me add in a future video? Send that to swardb@cud.edu, or of course, put a comment. You know, be nice about it. Don't send me mean comments. I'm trying my best here. It's difficult to talk to a video screen instead of talking to students because when I say something wrong, they immediately correct me. So it's like, this just lets me keep on talking. It's talking to a wall here. So please comment if you can. Again, I have a video for this. I have the general video. Now I'm going to make the video. We're actually going to go create a custom class in C++, at least the very basics of a custom class, so you can see how we can set up the binary tree under the hood, so you can get a feel for how that data structure is set up. Thank you, everybody. See you next time.